This video, we are going to begin our discussion of vectors, working our way into 3 space, which will be the whole point of Calc 3. So let's begin with the discussion, and we're going to piggyback off of the motivation assignment, talking about the need of something called a directed line segment. So let's begin with a different approach. A lot in geometry and physics, even in algebra, we measure things with just a single number. For instance, your weight can be measured with a number. Your height can be represented a number. Even in algebra and calc, we have slope is registered with just one number, right? In 2D, and this is kind of piggybacking off the motivation assignment, is that when we're in 2D, I can deal with that slope idea, right? If I have a slope of 5, that means go to the right 1, up 5, right? Up 5, right 1, rise over run. We can measure it with one number. But as physics requires, we work in 3 space, we live in 3 space, so we actually need more than just a single number. We actually need a lot more than that. So one thing that we have that we can think about is force. If I have a force, I got to push it with a certain amount of force. We'll leave it with that. And also in a direction. Same with velocity, right? Difference in velocity and speed. A speed is just how fast you're going in any direction. Velocity is how fast you're going and in what direction. Same with acceleration. They require a direction and then something we're going to call a magnitude. Magnitude, we'll call it length. This is the measurement of that force or that velocity. So for instance, if we're talking about velocity, we may say, okay, you are going 65 miles per hour in the north direction. That would be this idea of having 2 measurements. Right, so we can actually capture this idea of these 2 measurements with what's called a directed line segment, as you've seen in your motivation assignment. We can start at initial point P, so I'm looking here at this picture now, at P, and we're going to Q, and we actually register that with an arrow. I know it seems silly, very, very elementary, but this is a big foundational tool that's going to open up so much calculus for us. All right, so we have an initial point going to a terminal point. It's very important which direction with that arrow that you're going, because direction is a measurement here. All right, the directed line segment, which we're going to lead into, let's just go ahead and start calling them vectors. The directed line segment, we're going to call it a vector. It's the same thing. A couple of ways we write vectors. We can write PQ, and we put an arrow over it, and it's initial point, terminal point with the arrow. The arrow is important to tell us that it is a vector or directed line segment. You will also see this, and this is written down below. I can't write in boldface, but we actually can represent PQ, the directed line segment, as like, I'll just bold this up. PQ, I don't want you to do this ever on your paper. I would rather you do this. But in the book and in my typeset, I'm going to interchange these two often because I want to get you used to it. Okay, here's the deal about vectors, or directed line segments. We're going to call them vectors from now on. We just like to use the directed line segment because it makes sense into the transition for vectors. A vector doesn't live anywhere in 2 space or 3 space. It doesn't capture an actual point in space. It doesn't live there. What it does is it tells me how far to go in a direction and which direction. So this segment, I can move that segment here anywhere I want on my screen, and it represents the same vector as long as it points in that direction and has the same length. Now, we haven't talked about the length in this case. The length typically measures, like if this was a velocity vector, I know the velocity goes in that direction, but it also could have like 60 miles per hour. And what we would want to make sure was happening is that in space, 2 space, or what we're going to talk about 3 space soon, is that the length of that vector should be 60. Right? The length of it will tell us what the measurement is for the magnitude, force, velocity, acceleration, while the arrow just tells us which direction. Okay, if I take that arrow, if it measures that direction, pointing in that direction, and it measures 60 miles per hour, if I move that arrow anywhere on my screen, it still points in that direction, as long as I keep it that way, and it still has the length of 60. So you can tell down here, the equivalent directed line segments, this kind of leans into my idea. These segments here are all the same vector. The reason that they are the same vector is they all point in the same direction using our eyes, right? We can't promise that looking at it. And then looking at it, they all have the same length. Now, if I were wanting to show that two vectors were equivalent, I would need to show that they point the same direction and that they have the same length. It doesn't matter where they live. I can move them anywhere I want. All right, so here's some boldface for these vectors. So this is kind of what I was talking about. PQ is a vector in the plane. We can either write it like that, or they wrote it like this, the boldface V. We could also I write my V's like this. We could write our V like that if we wanted to, because we can't do bold when we're writing. All right, we could try, but I'd rather you not. So it's very important that you understand that vectors don't live anywhere in space. They can be moved anywhere around, and they're still equivalent. Okay, so with that, let's play with these vectors just a bit. We're going to get a lot of practice with vectors in the whole course. Okay, let V be represented by the directed line segment from 0, 0 to 4, 3. So I went ahead and drew me a graph. You can pause and do that if you'd like to. So I'm going to do that. So 0, 0. I got 4, 3. There's my vector. So even though they gave me points, I could move that vector wherever I would like, and it still represents that same exact vector. All right, I'll do the other one in a different color. Let's do it in blue. 2, 1 to 6, 4. Now, this one's going to be kind of, I drew my graph by hand. So it's going to be kind of hard to tell that they should have the same length and the same direction. But again, back like in high school geometry, we can't just use our eyes and say they are the same. Just like back then, you guys had to show that triangles were the same. We have to show these. You're not going to do a whole lot of this for me. We're going to find easier ways to show that two vectors are equivalent. Okay, so for V, do that in red. Okay, the first thing I want to find, if I want to find the length, I'm going to use what is called the distance formula. All right, so I'm going to write this down for you in case you forgot. Distance between 2 points it's just the Pythagorean theorem. It's the square root of x2 minus x1 squared plus y2 minus y1 squared. It's just the difference in the x's and y's, so it's the length of the triangle. So if I were to draw a triangle like this, all I'm doing is finding the length of each side of the triangle and then using Pythagorean theorem to find the distance. So we'll call this distance of, let me go ahead and give you the notation for that. The length of V, this is how we write it. It's going to be in the next video, but I'm going to go ahead and show you here. The length of V we show with these two bars. If you see that around V, they're saying, what is the distance of V? Which is going to be the distance there. All right, so we're going to plug these points in. All right, we got 4 minus 0 squared plus 3 minus 0. 0 makes it really easy for us. That gets us the square root of 16 plus 9, which is 25, which means that distance of the length of V is 5. Sorry, I didn't give you a whole lot of room on the sheet. I'm trying to save some paper. Okay, so we have that. Okay, we need direction for V as well. The way we could do that is if I'm trying to find the way a line moves, I would love to ask you this if we were in class, to see if you could recall. This would be the slope. All right, I'm going to put an M here let's flip that around. M was typically the way we said slope. I'm going to put the V in the subscript just to say, hey, this is the slope of V. Don't let that subscript trip you up. So remember, to find the slope, we subtract our y's on top, subtract our x's on bottom. So the slope of this is 3/4. Let me move this up just a bit. Cool. Next, be patient. There we go. So the slope here is 3/4. All right, let's do the whole thing again for u. There's my u vector. I put the bars around it to write the magnitude, which is the distance. So this is going to be the square root of 6 minus 2 squared plus 4 minus 1 squared is 4. So that's going to be 16 plus 9, which is 25, which means, okay, cool. The distances, the lengths, using the distance formula, are the same between vector u and vector v. So they have the same length. Okay, that's the magnitude part. Remember, vectors have two, or directed line segments have two measures. Length, which is called magnitude, and then the direction, and we were finding the direction of lines using our slope. So this is the slope of u, so I put u in the subscript, and I subtract my y's. If you forgot this formula, I should have wrote that up there. I hope you didn't forget this formula. There we go. And we got to plug those in now. So I got 4 minus 1 on top and 6 minus 2 on bottom, which gets me 3 over 4, which means they both vectors have the same length or magnitude. And then both vectors have the same slope, which means they go in the same direction. So we have shown, right, so let's write this. V and U are equivalent. We have shown that using the definition. All right, so that is how you show two vectors are equal. That is what a vector is. Remember, it's very important that you understand that a vector does not live anywhere in space or 2 dimensions in the plane. It just describes a direction and a magnitude, which is going to allow us to move this vector around and use it for different forces and applications that are going to be very useful for us.